The tech industry often describes AI developers as autonomous employees, digital agents you can hand a Jira ticket to and walk away from. But beneath the interface, a large language model is a stateless text generator. It predicts the next token. Without a structure to guide it, it is prone to hallucination, looping, and losing track of its original objective. This diagram shows the relationship required for a functional system. The equation is straightforward. Agent equals model plus harness. The model, usually a thin API wrapper like Light LLM, just supplies the raw text completions. Everything else you see here is the harness. The harness dictates exactly what the model sees, what commands it can execute, and how it remembers the past. To understand how production-grade engineering tools operate, we have to look past the prompt and study the harness design. Look at this terminal window. This is Aider, specifically version 0.86.3. It is one of the most widely used open-source coding agents available today. It operates through a series of specific architectural choices that often run counter to industry trends. Aider's architecture is built on 3 pillars. It is a format-based, single-agent, attended harness. It uses no multi-agent hierarchy or autonomous task planner. To see how these pillars function in practice, we are going to trace one specific command through the system, add type hints, and run tests. We will follow this data payload from the second the developer hits enter, all the way to the moment a successful Git commit appears in the repository. Along the way, the payload travels through 5 discrete architectural stages: intake, context, parsing, verification, and commit. By tracking this path through Aider's Python source code, we can examine the specific sequence of operations that enables agentic behavior. The journey starts at intake. Many agents attempt to detect when a task is finished so they can stop themselves. Aider uses a different approach. Its outermost loop is a standard read-eval-print loop, or REPL. It runs until the human operator explicitly stops the session. Once a command enters the REPL, it drops into the reflection subloop. This ring governs self-correction and is hard-capped at exactly 3 attempts. Inside that is the LLM-retry loop, surviving transient API timeouts with an exponential backoff capped at 60 seconds. If that innermost API loop fails, or if the middle reflection loop hits its 3-attempt cap, the system stops and hands control back to the human operator in the outer REPL. Enforcing these hard-coded loop limits prevents the system from entering the infinite failure cycles that can occur in more open-ended autonomous frameworks. Before the model can add type hints, it needs to see the code. But a 10,000-file repository is too large and too expensive to fit into an LLM's context window all at once. Aider addresses this through a component called the REPL map. REPL map uses TreeSitter to scan the entire codebase, extracting function definitions and isolating them from the rest of the source. It then ranks these symbols based on their relevance to the active chat. The system must ensure this prioritized list fits within the LLM's strict token budget. To find the optimal size, REPL map uses a binary search, repeatedly expanding and shrinking its boundaries until it perfectly fills the window. This dynamic context assembly is more precise than simply pasting entire files into a prompt. It treats context as a data compression problem. The goal is to provide a curated view of the repo that fits the model's limited attention span. Most agents use strictly typed JSON schemas for function calling, but Aider avoids this standard. Instead, the model outputs standard search and replace diff groks, bounded by specific text sentinels that it must emit precisely. When the response arrives, a deterministic string parser extracts the text between those sentinels and executes the file writes on the host machine. Using a regex-based parser instead of a strict tool schema avoids fragile validation errors. It allows the harness to function reliably across different chat models, regardless of how well they support native function calling. Once the edits are parsed, they are applied and committed to the local file system. Aider does not wait for a confirmation prompt before writing to disk. The system then moves immediately to verification. The harness shells out to a linter and runs the user's specific test suite to check the new type hints. Crucially, the system does not ask the LLM to judge the quality of the code. It relies entirely on external, deterministic tooling. If the tests fail, the harness captures the exact compiler exit code and the raw error log. This failure triggers the feedback loop. The raw error log is fed back into the reflection ring as the next input prompt, giving the model the exact context it needs to fix the bug. By binding probabilistic text generation to deterministic compilers, the harness can verify its own output through real-world execution. This execution process relies on a specific design choice. Aider does not use a secure execution sandbox. Shell commands execute directly on the host machine. There are no virtualization barriers or containers separating the agent from the operating system. The memory structure is equally direct. Aider rejects complex vector databases in favor of a flat system, one markdown file for chat history and local Git commits for code state. If the chat history grows too large for the context window, the system uses in-place compaction to summarize the text rather than moving data into secondary storage tiers. The lack of a sandbox is an intentional trade-off. It assumes a human operator is present on the loop, relying on explicit confirmation gates only for high-risk shell commands. By using Git as a rollback surface and keeping the human involved, the architecture prioritizes execution speed and simplicity over autonomous isolation. Let's trace our add type hints prompt one last time as it moves through this entire pipeline. The prompt enters the REPL, paired with a context window, filled by repo-max binary search. The LLM generates a structured search and replace text block, sidestepping the need for JSON function calling. The parser applies the edits to the local files, which are immediately recorded by an automatic Git commit. Verification begins. The linter fails, and the harness captures that failure, feeding it back into the bounded reflection loop for a second attempt. On this second pass, the linter passes. The reflection loop collapses, and the system returns to the outer REPL. This sequence of loops, parsers, and deterministic filters is what enables a probabilistic model to function as a reliable engineering tool. There is a clear distinction between the concept of an unbounded, self-governing intelligence and the reality of a production coding agent. The purpose of a harness is to constrain the model's action space and force its predictions through deterministic checks. By limiting autonomy and enforcing strict self-correction caps, this architecture provides a level of practical utility that open-ended agents currently struggle to achieve.